Today we shall discuss about most important parameter of MOSFETs, that is resistance from drain to source, that is called RDS. We have taken four MOSFETs, different types of MOSFETs, popular MOSFETs, and they were connected to some supply, and then gate drive, positive gate drive by some resistance. All the four are similar circuit. There is absolutely no change. We are given some ammeters measure the current, and we have put some voltmeter to check the voltage drop across the load. This is the load, and this is of course the switch, and how much voltage drop is here is measured by this voltmeter. So all the four systems setups are like that. We will go into one by one for their function, one by one for their function. The first one we would like to discuss is about IRF540N, which is a very popular MOSFET, which is for low voltage applications like this. And then what we are interested to know about is RDS on. RDS on here is 22 milliohms, that is 0.022. Now let's look at this section. This is Z44, and when we try to simulate this, what we find, all are 0 here, and the full voltage, 12 volt full voltage appears across the switch because we have not given any gate drive. Once we give the gate drive, what we find current is about 9.83, and there is a voltage drop across this is 0.21. How is that? It is, the current is 9.83. So power loss is I square R, that is I into 0.022. What we had seen the data sheet, it's about 1.9 watts. And in voltage VDS, this in the practical circuit, what we find here, VDS, the same thing, VDS into I, the current, that is 0.21 into 9.83 is equal to 2 watts. So in both the cases, we find there is a power loss of around 2 watts in this MOSFET. Similarly, we will look into others also, and we'll watch how the power loss affects the performance of the MOSFET. Now let's see another MOSFET, which is IRF540. This also is a very popular MOSFET, N MOSFET. All we are talking about, all of them are N MOSFETs. So when we power this, since there was no gate drive, the full voltage is appearing here. And when we switch on this, what we find, there is a voltage drop of about 0.39 volts, and the current is 9.68. So as per the formula, I square R, 9.68 into 9.68 into 0.04. What we have seen, its data sheet is 0.04 is its RDS on. Let's check that. This is IRF 540N. RDS, what we find here is 0.040 ohms at a gate voltage of 10 volts. So I square R is I into 0.04. The R, I square R, is equal to 3.74 watts, or the voltage drop that we find here, 0.39 volts, into again the same current, 9.68, we get 3.7 watts. Both are same, almost same. There will be very, very marginal difference, but then both the cases are same. Let's watch another pop IRF644, which is the high voltage. The VDS is about 10 to source 250 volt, it can withstand. Of course, these are all maximum voltages. We will discuss all of them as to what is the safe voltage to be operated. But in the RDS here is 0.28 ohms, and it has a capacity of having a drain current of 14 amperes. In all the cases, we have limited the current. When you look at that MOSFET, IRF644, and since again there is no gate drive given, so the full voltage appears across here. Now once I give the gate drive, I find there is a voltage drop of 2.27 volts, and the current is, what we find, the current is 8.11. So I square R, 8.11 into 0.28 is what we have seen from the data sheet, is 0.28 is equal to 18 watts. And the same thing, or the voltage drop across this, and the current V into I is equal to 18 watts. So what you can find, how the large difference we have been watching of different types. Higher the voltage, the RDS become high. That is what the conclusion that we can draw. Here is another popular MOSFET. So this is IRF250. Voltage is 200 volt and capacity of 30 amperes. And it has RDS of 0.08 ohms, 0.085 ohms, 0.085 ohms. Now when you look at this IRF250, same thing, open circuit voltage, full voltage appears across this MOSFET, And when we switch it on, we find voltage drop is 0.80. Or if I take the data sheet, in data sheet, the current here is 9.33 into 9.33 is I square into 0.085, what we found in the data sheet, and which is about 7.4 watts. Whereas same calculation, the voltage drop is about zero point 0.8 volts, and so V into I, zero point 0.8 is equal to 7.4 watts. So all that what we find, how the losses on the MOSFET is increasing while the RDS is increasing. So more the loss means you need very big heat sink to dissipate that heat. So that is what is one of the very important parameters that we have to observe. Now let's watch all of them in a comparison mode. I see what we have done. We have given the same voltage and we find nearly the current is same, but see how the power loss happens here. In this Z44, it's about 2 watts. In this 540, it is about 3.7 watts. In about 644, it is 18 watts, and in the IRF250, it is 7.4 watts. So how you see how much difference is happening. Now, for example, this one having so much of power loss, so unless you use very high heat sink for this, it is not advisable to use this. So based on your design, what is your voltage and current requirement? Based on that, we have to choose the. So one has to choose based on the voltage, current parameters, and most importantly the RDS parameter, and most importantly for the RDS. We shall discuss in the next part another important parameter, the gate capacitance. There is a capacitor in the gate for all these MOSFETs, but then how the capacitance, value of capacitance plays an important role also